In the previous lesson, we introduced the concept of mode superposition. It is an approximate method, but with the proper setup, it can be very accurate and extremely computationally efficient. Let's now take a closer look at the details of the method. As we introduced in the previous lesson, this method is similar to how it is applied in beam theory, where the displacement of a combined load is the sum of the displacements of the individual loads. Now getting back to dynamics, specifically mode superposition, we express the displacement shape as a linear combination of mode shapes. Here we will take the first shape times a factor, add the second mode shape times a factor, and finally the fifth mode shape times a factor. And you can see we can represent ever-increasing complex deformation shapes by adding in more and more factored mode shapes. Now technically these factors are called the modal coefficients. So keep in mind that the method of mode superposition is only valid for linear behavior, not nonlinear. So when is it applied to a transient analysis, the assumption is the response is linear, so no nonlinearities are permitted. When the method is applied to harmonic, well, harmonic response is already a linear solution by the nature of its formulation. We will discuss more details on harmonic analysis in the next section. Now let's use a diving board to illustrate the concept of mode superposition. We will look at only 3 of the diving board's modes, specifically the first, the second, and the fifth, since these 3 are dominating in the out-of-plane displacement, meaning the direction that the diving board is most flexible and meant to displace. When the method is used in a practice on an actual structure, we typically do not exclude shapes, as the software and the computation determines how much of a particular mode contributes. In other words, we leave it to the mathematics to determine how much contribution for each mode. Also, keep in mind that even though a diving board typically has very large displacements that would violate the linear assumptions, we're using it since it's visually easy to illustrate this concept. Here is the first mode shape animating, and the deformation is expected, as it is the first bending mode. Here is the second mode shape, which is the second bending mode, and notice it is increasingly complex with a hump in the middle. And similarly, the fifth mode shape is more complex still with a second hump. So let's think about this. If we need to capture just the diving board bending down gradually with no humps, as if a diver is standing on the end, which mode shape do we need in the solution? Well, the first one would dominate, right? And we would not expect to have any wavy displacement or humps that we would see or get from mode 2 and mode 5. Now let's explain a bit of the math that governs the mode superposition method and then come back and illustrate it back on our diving board. This is the general equation that relates the physical degrees of freedom, which are the displacements at the meshed nodes, to what is known as the modal coordinates. The equation just states mathematically that the displacement vector over the model is equal to the sum of the mode shapes, or eigenvector phi, times the modal coordinates y for that mode. This sum can include 1 to all the modes. The more modes included, typically the more accurate, but sometimes very good results can be achieved with a limited subset of the mode shapes extracted. Now, how many modes that need to be included all depends on the complexity of the displacement shape that we are trying to capture. So the first step in mode superposition method is to solve the modal analysis and have the eigenvectors or mode shapes available. Next, the modal coordinates y are computed by the solver. These modal coordinates are the scale factors that multiply times the eigenvectors to scale the contribution of each mode shape to the resulting final shape. So in a mode superposition harmonic or transient solution, the unknowns are the modal coordinates. Once the modal coordinates y are computed for each mode, they are multiplied by their respective eigenvector phi, and the final displacement shape is computed. In mode superposition harmonic analysis, these coordinates will be multiplied by the sinusoidal function. But in mode superposition transient, we will actually have a time-varying listing of modal coordinates, where each curve is the graph from a particular mode, and we can see how it changes and its contribution changes over time. So while the mode superposition method is just that, a method, it can be applied to different simulations, such as harmonic, transient, and others. We will focus on the harmonic implementation and now touch upon how the equations of motions are solved for the mode superposition harmonic. We'll go into more detail of the math and equations in this section on harmonic analysis. For now, we'll focus on the higher level aspects, specifically comparing the full harmonic equations with the mode superposition equations. The full harmonic equations of motion is expressed as shown. The derivation of this equation will be covered in the section on harmonic analysis. But for now, we have the mass m, the damping c, and stiffness k matrices of the system. Omega is the imposed circular frequency. F1 and F2 are our real and imaginary forcing vectors. Finally, U1 and U2 are our unknowns, that is, the real and imaginary displacement vectors. These unknowns are coupled, meaning there are multiple unknowns per equation, and in order to solve these equations, we will need to use a matrix solver, which is computationally expensive. Now, if we are to convert the equations to the modal form, which we will discuss in details in the section on harmonic analysis, the equation looks like this, where again the uppercase omega term is the imposed or excitation circular frequency. Lowercase omega sub j is the natural circular frequency at mode j. Zeta sub j is the damping ratio of the mode j. F sub jc is the loading vector in modal form, and it's also known as the modal force. And finally, y sub jc are the modal coordinates, and they are the unknowns which we must solve for. The number of the unknowns is just the number of modes. We solve this uncoupled equation easily for each mode j, and later we multiply these times the eigenvectors and sum them to compute the total displacement. Recall this equation that relates the physical degrees of freedom to the modal coordinates. Notice that all the computationally expensive matrix algebra has been done in the modal solution to compute the eigenvalues and eigenvectors. Just some simple math is done now to compute the modal coordinates, and hence long transients and harmonic response runs may be analyzed inexpensively using this technique. The key takeaways are that the application of the mode superposition method to solutions such as harmonic, transient, or other has fewer degrees of freedom during the solution after the modal solution, and the equations are uncoupled, resulting in a computationally less expensive solution. Now let's go back to our diving board example. Recall here our first three modes with their respective natural frequencies. Now, if we put a harmonic force or sinusoidal oscillation on the tip of the diving board, that is at a frequency that matches the first natural frequency, we will be exciting that first mode shape. And what do we expect to be the harmonic or forced frequency response of the diving board? Which of the three shapes will dominate? Here is that harmonic response, and it's pretty clear it is dominated by the first mode shape. So what would we expect for the modal coefficients? Here we can see at the excitation of the frequency of around 1 Hz, these are our modal coefficients, with the first mode shape of 1.01 Hz dominating. So going back to our equation, we can write that mode shape 1 times modal coefficient 1 plus mode shape 2 times modal coefficient 2 plus mode shape 5 times modal coefficient 5 gives us our total deformation shape at the harmonic response at that excitation frequency. Now recall, we're only illustrating this with 3 modes, but the summation would be over all the modes, not just these 3, and all the modes that were requested during the solution. So clearly, based on these coefficients, to make this final shape in our harmonic response, we really need mostly the first mode shape. Now we could repeat the same exercise by exciting the diving board at its second natural frequency, and we would see the same trend. that exciting at the second natural frequency, our highest mode coefficient goes with the second mode. But what if we excite the structure at an arbitrary location and arbitrary frequency that does not coincide with the natural frequency? We would expect the combined shape to not be dominated by a single mode shape, and that is exactly what we see. In this example, we excite the diving board around 2/3 of the distance to the tip, and we look at the response to an arbitrary excitation of 13.1 Hz. Here we see the harmonic response from this excitation, and here are our modal coefficients, which are of fairly similar in magnitude. So to achieve this unique deformation shape, it takes a bit of all of these three mode shapes. Finally, as we discussed prior, if the mode superposition method is applied to a transient analysis, our mode coefficients will actually be a function of time, and you can clearly see this in the curves, and also how relatively some modes may contribute more to the overall deformation shape than others. But again, this will all depend on the loading environment and the particular structure we're analyzing.